actually starting to build the model, we want to know and understand what data, what evidence is actually available and what is not available. If we don't have sufficient data to support our model, to feed our model, you know, so what credibility it will hold. So it is very important to actually first do a literature search, literature review for that, and to know what all is actually what all evidence is actually available. For situations where essential data are missing and assumptions can't be made, supplemental studies may need to be conducted before actually completing the model. Okay, moving on to next step. Once you have done your evidence and knowledge and data gap, you have analyzed the data gaps and you have analyzed how much evidence you have, you need to do the collection of inputs. So collection of inputs are mainly in three domains, these three domains: clinical inputs, epidemiological, and economic inputs. Okay, within clinical inputs, you can have the treatment pathways, which can be defined in the form of transition probabilities, disease progression, remission, death rates, all these things. Then you can have efficacy data, you can have clinical outcomes from the clinical trials and utility values for each health state. So these are broadly the clinical inputs. You have epidemiological inputs. Here you can have total the number of population which will be covered actually by your drug, then rate of disease, subgroups by age, sex, severity. So maybe the clinical inputs might differ based on the subgroup. So we need to analyze that as well, and we need to consider that as well. Now, the third is economic input. So, in economic, again, you need to have the resource utilization, how much the resources are being utilized, the drug cost. You need to have the unit cost for each resource utilization, hospital cost, surgical cost, adverse events. What are the adverse events? What event cost, management cost. Uh, in budget impact, you do have market shares as well. Okay, and then you have contracted price adjustments if there are discounts available on the drug with respect to from certain perspective, based on certain perspectives, so that also need to be included in data collection. Now, after doing all this, you need to start building your model. What do you do? How do you do? You first draft a storyboard of the model. Okay, you lay out the flow of your model and content. You can either use a PowerPoint presentation or an Excel for that. Okay, you actually be building a flow, like what all I include in the model. Then you draft design document. You text document. A text document is basically um, designed here. It can be a Word document where you will describe what is the model objective, what methodology you are going to adopt, what results you are going to include, what assumptions you are going to take. So just before building the model, actually you need to write it down, right? You need to be clear on all these things: the methodology, the model objective, the results which you are going to get, actually include in the model, what all assumptions you are going to make, how the patient flow you are going to show, all these things, and how the person can actually navigate through the model. So all these things, and include all the details of the model design, including calculations and equations, in this draft design in design document. So this is basically a guide to your Word document guide to your model. Okay, and it's a good practice to have it, because once when you are actually giving your work, your model to somebody, uh, he might not be it would be actually easier for him or her to navigate through the model with the help of the document. So ever in a life, if you are actually building a model from scratch, always try to draft a design document. Always try to have a text document where you can actually include all these topics. Then after that, you start actually programming the model, the third part, which includes actual page by sheet by sheet on Excel, or page by page. You start constructing the model according to your storyboarding. So you have already storyboarding you have already done, so you know what all things are going to be there in the model, and you start programming it. Set up your health states and transitions, populate the all the data, cost, and utility value, and then program the model. After this, once you've done with your programming, you calculate the results. You run the base case, calculate total qualities and total cost and incremental cost effectiveness ratios in terms of your cost effective model. Okay. And ICER is compared with your willingness to pay threshold to assess the value. Now, once you have your base case results, you conduct sensitivity analysis also, one way probabilistic sensitivity analysis or scenario analysis. I've already discussed all these yesterday, so I'll describe it more into the model. Then after that, once you're done with your results, once you're done with your your sensitivity analysis, the next step is to validate the model and revise. So validation is a crucial step in building a model to ensure it is accurate, it is reliable, and it is credible. Okay. And there are two types of validation. There are mainly three types of validation: internal validation, external, and cross validation. Internal validation means check if the model works mathematically and logically as you can think, right? So make sure that mathematically there is no error. If the cost of your intervention is higher, it should be reflected same way in the model also. Okay. External validation: check if the outputs produced by the model matches with the real world data, published studies, right? So if you have real world data, real world published studies already available for your your intervention, it's always good to actually cross tally them, match with them, so that it provides a better validation to your procedure, to your programming, to your model, that yes, the model is giving us the desired results. Cross validation: check if the model produces similar results to other independent models if of the same condition. Okay, if the model produces similar results to other independent models, so the model which is like other models, same as quite same as external validation. So you refer other models for the results if they are producing results in a similar fashion, similar lines. So this the initial base case results give you a impetus to basically do more model revisions, and validation actually helps you to think, and it gives you assurance that your model is more reliable and is more credible, and you can actually then supplement your model with further research to strengthen the model. Okay, and to strengthen your inputs and then results. Okay, so these are mainly 7 broad steps when you think of doing a you do think of creating a model. Now, example. I'll show you one example now. Again, the decision tree analysis. I've already covered it yesterday, so I won't take much time. Decision tree is basically a tree-like structure where you have structured approach in decision making. You go from your chance node to the terminal node. So there are different types of nodes. Uh, Decision node, which is your um, decision node in square, which starts at the beginning of your decision. Then you have chance nodes, which reflects the possibility of probabilities, like what can actually happen. Then end node represents the final outcome or payoffs, where you actually apply the payoffs. Okay, so you have different branches. You assign probabilities and you assign payoffs. These are three main things. In conducting a decision analysis, you define again the same. You define your problem, structure your model, assign payoffs, conduct your expected values, and then make decision. I won't go again into the same thing. Defining the problem. you want to know what you want to solve and define the success criteria. Basically, you define your comparators, your success criteria, your outputs which you want to include, all these things. Okay, then you identify your comparator. You want to include your comparator drug, or you want to include a do nothing option, not doing anything in terms of any treatment. If you want to include any treatment, and option A, option B, or do nothing and let the patient flow with a natural progression. This could also be a possibility. Okay, then structure the decision tree based on your uh, possible events and outcomes in a hierarchical format. Okay, so this is an example. Another example, you have hip replacement patients. Okay, then you can either go to parent treatment or conventional treatment. These are two choices available. Then either with heparin, either the patient develops DVT or no DVT, deep vein thrombosis, or no DVT. With DVT, either the patient is having bleed or no bleed. Similarly, without in case of no DVT, either there is bleeding or no bleeding. Similarly, with the conventional treatment, so you will assign probabilities to chance events basically. So the estimate the likelihood of various uncertain events occurring based on the historical data, expert opinion, or statistical analysis. Sum of probability should be 1 at each chance node, as I told you yesterday. Okay, use evidence based data wherever it's available. Sensitivity analysis you do to see the uncertainty around your inputs. Okay, for example, if historical data suggests 80% success rate for a new screening program and 20% failure rate, these probabilities are assigned to corresponding branches. So if we have a screening test and we want to assign the probabilities, 80% success probability, the failure would be 20%. It has to be 20%. Okay. Now, once the decision tree is structured, now we have these cost and utilities for all the branches we had. Cost for low molecular weight heparin, for your conventional treatment, for your DVT, for your bleeding. Okay. And then you have DVT with heparin, the probabilities. Okay. DVT with heparin is 0.14. No DVT with heparin would be 1 minus 0.14. Similarly, DVT with conventional treatment is this, and no DVT with conventional would be 1 minus this. Okay. Now, moving on, you assign the payoffs, the cost, and your benefits, non-monetary values like qualities or uh, any patient satisfaction, or whatever your parameter is you want to include in the analysis. Here, now see, we have actually put up all the cost here. Probabilities. So you had two branches. Probability 0.14 for DVT, and with no DVT, it would be 1 minus 0.14, so 0.86. Now, conventional treatment with DPT was 0.25, and for no DPT would be 1 minus 1 minus 0.25, which is 0.75. Okay. Now, probability for bleed and no bleed, again, the same thing has been done. Okay. And at the end, the qualities and the payoffs, basically either in the cost payoffs or the benefit payoffs, are applied at the end, at the terminal node only. So the quality for bleeding with low molecular weight heparin is 0.65. No bleed would be 0.7, 0.951, like this. Okay. So if you broadly see, we have divided into 4 major branches. One with DVT, heparin with DVT, heparin, no DVT, conventional treatment having DVT, and conventional treatment without DVT. So A, B, C, and D. Now we are going to do the payoff, the calculation. Yesterday I told you the calculation we do starts from the terminal node. So you have to start calculating your payoff, the cost and qualities from your terminal node. And this is your terminal node here. Okay. So how would you do it? For point A, you multiply your poly value with the probability of that branch. 0.65 into zero point 0.1. 0.65 into probability of bleeding. 0.1. Similarly, 0.7 into 0.9. 0.1 into 0.95. Okay. So you are, for point A, you will calculate bleed plus no bleed. Total qualities would be 0.695. And similarly for point B, 0.95 into zero point 0.1 plus 0.1 into 0.9. What we are doing, we are actually, just consider, we are actually wrapping up the model because we want to finally make the choices between these two. So we are adding up total qualities based on their probabilities. Okay. Once we are done at this level, we had calculated the cost for A, B, C, and D. We will do the same exercise for this level. Now you will have total qualities for A, for B, for C, and D. Means you have total qualities for DVT, no DVT, for heparin, and similarly for conventional treatment. Now the next step is this. See, what I told you. Now we have qualities at this level. Now we want to again do the same. We want to do probability with quali, multiply this probability with the quali plus this probability with quali, and you will get total qualies with respect to heparin. Similarly, you will do multiplication of DVT probability with the quali and no DVT with quali for that no DVT, and you will add it. So this will give you total qualities for your conventional treatment. The same way you have to do for the costing. Okay. And then see the 0.695 for point A and 0.99 for 95. These are again multiplied with the probabilities for the respective branches and then added, and this is the total quality 0.953. So this would be actually the total qualities for LMV heparin. Okay, and similarly qualities for conventional arm would be 0.69 multiplied by the probability of DVT and 0.995 multiplied by the probability of no DVT for conventional treatment. So this would be the total qualities for conventional treatment. So these are the final qualities for each one of them, for heparin arm and for conventional treatment arm. See, right? And then you have to you can do the incrementals. Okay, so expected values would be calculated. The same thing is explained here. It's just in a formula, right? So moving on. Now, once you are done with it, you perform the sensitivity analysis. I'll just skip it and I'll show it in the Excel file. Okay, let me show you actually the Excel now. Is the model visible to you?
Yes, Akanksha.
So this is a model. This is not the same model. Uh, this is for basically migraine treatment. Okay, the principle is same. I have given everything in the model. So what actually we want to do is we want to compare the oral sumatriptan, which is a drug for management of migraine attacks. We want to compare it with oral caffeine in treatment of migraine attacks. Okay, so this is the model structure. If you can see clearly, let me just zoom it a bit more. Let's understand the flow. So for this, decision tree was used. Okay, now what? How the patients are flowing? Like what is the model flow here? Model structure here. The patient who have migraine attack, the decision could be either they can take sumatriptan or they can take caffeine. Okay, either they have relief after taking each one of them, right? Relief or no relief. Within relief, either there is no occurrence of migraine or there is occurrence of migraine attack. Okay, then if there is no relief at all, they they endure the attack, and or they can go to emergency department for their further treatment. If they go to emergency department, either they are getting better or they are still remaining hospitalized. So this was the general approach which was observed in migraine attack, the patients with migraine attack, right? Now, similar the flow is with patients who are taking caffeine. Here you can see the probabilities are assigned to each one of them, right? And for both, the probabilities are different based on the literature. Now, when you're constructing a model, first step was to actually know what you want to do. So we know that objective is basically to compare the oral sumatriptan, to have an economic evaluation of oral sumatriptan with your caffeine. Okay, you you divide your model into different sheets, or you can actually have it in one place. So for ease of understanding or ease of telling you the concepts, I have made the model in one place only. Okay, so in introduction, in an introductory slide, usually introductory sheet of the model usually have the title of the study, what is your objective, you tell a bit about the disease, or why your intervention is important, and what is different which it actually provides in comparison to the other comparator which is available. You define your intervention, your comparator, you put up all the model assumptions which you are actually thinking of to include in the model. Okay, and then you actually defines the outward parameters which will be included in the model, and list of all the abbreviations you think when you will be using in the model. So this is basically what you will report in your introductory slide. Now let's go to the actual model. So from the literature, we had probabilities the for both our arms. Okay, so probability, so we have sumatriptan and your caffeine. You have either there is no uh, let me just maybe should I put it up here also to show you. Okay, now this is fine. Okay, so what all branches you had? No occurrence, no reoccurrence or reoccurrence, endured attack or relief, or hospitalization. Let's Okay, so probabilities are assigned at the terminal, at the end. Probabilities are available for the terminal nodes at the end. Okay, so these are the probabilities: 0.331 for no occurrence, For reoccurrence, it's 0.22. For endure attack, it's 0.40. And for relief, it's 0.3035. And for hospitalization, is 0.009. Okay. Then similarly, we put up the probabilities for your caffeine. Same for the last year, for your last terminal notes. Now you have the cost. Basically, you have, I've provided here here the cost for you, but actually you need to actually calculate the cost. How much cost would be incurred if there is no recurrence? How much actually the cost would be incurred if the the if if the attack happens again? Okay, and this would be based on the management which is being followed by the physicians, right? So you need to ask, maybe there is literature available which directly says that this is the cost available for management of attack migraine attack recurrence, right? Either you can leverage that, otherwise you have to ask the key opinion leaders, the doctors, for what they practice, because the practice could be different for different geographies, right? Maybe some molecule is available in geography A which is not there in B, and then they are prescribing different therapy, different drug. So the cost can vary based on the practice of local, based on the local practice, based on the physicians which who are practicing in that geography. So it's good to verify or validate the cost from them. They won't be able to tell you the cost exactly, but they can actually tell you how do they manage their patients with in case of no recurrence or recurrence if they are in your attack, or how do relief they get, right, in all these situations. And then you have uh, either you have two costs: societal cost and health cost. So basically these are the indirect costs also I've added. Okay, and these are the direct costs for the management. Now total cost would be, you add the both the indirect and direct cost to have the total cost. Okay, this is for your sumatriptan, and similarly I've done for your caffeine, right? Now you have your effectiveness. On the similar line, we have the effectiveness. So effectiveness here in this model was uh, uh, reported in two forms: either the case averted, like did the patient not suffer, like did the patient not have any further migraine attack, or the quali loss, qualies. Okay, then total effective. So based on what we select, effectiveness measure, the outcome will be selected. Let's discuss it further. So basically these are the quali values with each, quali's value with each. Okay, let's not call it colors, it will be confusing. These are the quali values. Okay, qualies for each state, and then the total effectiveness would be whatever the parameter we have selected. So we have selected effectiveness measure, we have selected as qualies, so this is the qualies will be reported. Okay, so again I was doing the sum. So I was multiplying, in the slide deck I showed you, I was multiplying the probabilities with the cost at each terminal branch, and then multiplying the cost with the probabilities, and then adding those. The same I'm doing here. The formula I used is sum product, but sum product, what does it do? It multiply the respective cells in both the arrays, and then it sum. So it does the product of the two branches, two arrays which you have selected, and then it sum all of them. The same thing it's doing here. Okay, similarly for effectiveness, it's multiplying probabilities with the effectiveness and giving you the final expected value, right? Okay, now for caffeine, similarly we have done, you have health cost, you have societal cost, total cost is mentioned here, and here you have the final cost, uh, expected value for your caffeine, and here you have the expected value for your qualities, basically expected qualities for your caffeine, right? Base case would be the base case result. This is the base case basically from what we have gathered from literature. This is the base case. You will have incremental outcome as intervention minus your comparator. You will get incremental cost here. In this was the cost with your intervention. This was the final cost with your comparator, and difference would be incremental cost, and here the this would be your incremental policy. Okay, and then this is your incremental cost effectiveness ratio. So it shows that you are basically saving you the by per you are paying less. You are paying less with your intervention, so you're basically saving on money. You are saving $5. You are saving 7,768 dollars per poly gain. You are paying less with your intervention. So this is what it shows. This is a very basic uh, example, right? Now, in the model, what you want to do is it's always good to now here this is your base case model. Now I want you to understand how we will do the one-way sensitivity analysis. Okay, so for one-way sensitivity analysis, what we do is we change one value at a time, and when we report the final outcome. Okay, so what your input values are? Your input values are probabilities, your effectiveness, your qualities, right? For either one of them. So maybe you can change your probability of your no recurrence. Maybe you have two literatures, and uh, one was reporting the probability something, and other was reporting the probability to be something, and you want to actually test which one should I use. So maybe you can do a one-way sensitivity analysis to see how the result would vary using the two sources. Okay, or maybe what you do is you want to just change 20% up down of your input and see how much it will, to see the uncertainty around your input. You can see how much it will vary your final outcome. Okay, and so let me just put a value here. Let me just maybe put the value of, let me first save this one. With base case, or with base case, your value was this. Okay, now what I'm going to do, I'm going to change the value to 0.40 and see how the results are changing. Okay, it is still going in the same direction. I've increased the value. Now let me just reduce the value. The base case was zero point 0.7. When you actually increase the value to zero point 0.4, it was showing you, still it was showing savings minus 5,899 dollar per quali game. Okay, and when you are reducing your sumatriptan no recurrence probability, it is also it is also showing you results in savings, cost saving side only. Similarly, what you do is you change your probability, you change your different parameters, not all parameters, key parameters which you think might affect your results, or you think which have more uncertainty around them. You do you do you don't do actually one by one. There is VBA codes to actually do this for one-way sensitivity analysis. So it will you actually list down the key inputs, and then they will the VBA code. The code will actually, what it will do, it will vary the parameters high and low, and it will give you the ISOs, and those ISOs are actually plotted on the tornadogram from upside down. So the one which is having the wider bar will be on the top, and then rest will follow, which I showed you yesterday also. Right? Let me show you again. See, this is an example as I showed you yesterday. So you will have the different risk, different your variables here listed, and because your base case result is minus 7,000, your 7,000. Let me see what was our base case result. It was seven minus negative 7,767. So here your vertical, the zero line would your vertical line would actually start from minus 7,000. Okay, because that is your base case results, and the variation of each parameter would be plotted on a vertical, on a horizontal bar graph. It can be done on horizontal bar graph. You do one-way sensitivity plus or minus for your key variables, and then you plot it on your bar graph to actually plot a tornadogram. We do have VBA commands for it. We don't do it manually usually, because it's a tedious task to do manual, change the values manually and then plot it on a graph. It takes time, so therefore we give the command to command to the Excel, and we mention the variables which needs to be used for your tornado or for your one-way sensitivity analysis. It will do the one-way sensitivity analysis using 20% plus minus values or based on the standard deviation, and then it will give us this tornadogram. Okay. Now I'll move back to the model. So this is how we do one-way sensitivity analysis. Hope it is clear. Now comes the probabilistic sensitivity analysis. For probabilistic sensitivity analysis, you actually have to first determine the uh, distribution. So on the right side, I've actually what I've done the values, base case values I've mentioned, not the base case. Basically, this is the base case values, and here stochastic is the basically values which are going for PSA model. Okay, I have because usually what we do is uh, we uh, we put a command for PSA, and there are number of iterations which have to be run. It's not one time or two time or three time or 10 times, like thousands of iterations, thousand of simulations, like thousand times the model has to do the analysis based on this approach which I am showing you. So I am showing you actually what a VBA command does at the background, and maybe that this will actually help you to understand how PSA is done, and what we do as a scatter plot, how to interpret that. Okay, so these are all your inputs in terms of probabilities, cost, and utilities. Okay, and these are the value which are actually going into the model. Now you have two columns here. One is deterministic. These are the hard coded values, which are basically our inputs from the literature or our sources basically. And this is for PSA. So when we will choose our, the model type, if we want to actually, we will do the PSA, we will use stochastic as a type of model. So what it will do, it will pick up values based on our distribution. Okay, these are different types of distributions which are used for different types of our input variables. Okay, and there is a science to it. And when we are actually, writing our model document, we have to actually report that what all input variables we are going to have, and what distribution we are going, if we are doing probabilistic sensitivity analysis also, what all distribution we are going to take, right? And then based on that, we will we our values will be calculated. So what it is doing, it is basically uh, based on our our distribution, it is actually calculating the values from your random distribution. This is the random distribution you have. Okay, and you get value. So every time I'll every time I'll click enter, you can find these values are changing, right? Every time I click enter, these values will change, means our inputs which is going into the model will change, and based on that, our final results will change. Okay, so we have probabilities, cost, and utilities. So for probabilities, I'm using beta distribution. Usually, beta distribution is uses, and for cost, either you use log normal, or if the cost, you want to keep the cost fixed, so you don't put any distribution, and you keep the distribution fixed. You need to actually reason out why you are doing what. Okay, beta, gamma, log normal, these are different types of distribution you use. Now, let me now put my model type to stochastic. The soon I did stochastic, my model results are updated. So now you're showing, now this is showing us the savings of mine. Like we are spending 34,000 less to gain an extra quali, right? And this is one probabilistic sensitivity analysis. So the model has changed all the values simultaneously, and based on that, this is one ISO you have got for PSA, right? The model have to do, now to see the robustness of your model, you will have to do this process like thousands of times. Okay, and after those thousands of times means you will have these thousand of what you call your ISO values, your incremental cost and your incremental polys, thousands of values you will have. So what I have done is, for you to understand, I have actually done it not thousands time, but few iterations I have pasted here, like with each click of PSC, because the random numbers are generated, and using the distribution, the random numbers are generated, and then random after random numbers you are getting different ISOs. So based on that, actually based on those final results, I have pasted those results here. This is something which I have calculated to basically show you, and these are the results I have pasted from the PSA. Okay, now based on these results, I have calculated the incremental cost. Sorry, this is incremental cost, and this is incremental qualies. Okay, this is 25 times I've done, but then the number of simulations you mention in your code, it will actually do the model will run PSA those number of times, 1,000, 10,000, to to 80,000. So it based on the number of iterations you want to run. Okay, and once you get these results, it will calculate the incremental cost and incremental polys, and then you plot these values on your scatter plot, the plot which we discussed yesterday. Okay, so each value is plotted on this graph. Scatter plot, what is scatter plot? You have incremental polys on your x-axis and incremental cost on your y-axis, and you plot your incremental cost and you plot your PSA results on this graph. Now, what is it showing? Only 25 iterations, so you won't be able to actually make a point out of it, make a conclusion out of it. But all the results are scattered, right? They are not concentrated at a place. All the points, all the 25 points are not concentrated. They are all scattered, and they are showing that your cost, the incremental cost, is mostly negative here, right? And the incremental polys are also, like, you can't make out of incremental polys because the difference is very very minute. You can't make out of it, but yes, you can surely say that you're saving on cost in most of the points. Like out of 25, you can say 70% or 80% of points lying uh, points are actually saving you the cost, right? So this way you actually do your probabilistic sensitivity analysis. This is a basic way to do it. I have just shown you actually how the how the commands, how the VBA commands in Excel, or how R does it in the background, right? Once it is done, you plot all these PSA results along with your base case results. So if we see the base case result, what it was, let me just put the model type back to deterministic. So you had 5,800, and so you had -3 incremental cost and additional of 0.006 poly. So again, it would lie somewhere in the quadrant. In which quadrant? You tell me. Now you tell me. Enough of me talking. You tell me, if we are saving $3, and if we are saving $3 and if we are having gaining additional of 0.0006 of polys, in which quadrant will our base case point lie? Answer. Yes, there have to be WTP threshold also, but I have not created because the number of iterations were not enough to actually do analysis, complete analysis. Second. Okay. Second. Everybody with second? Yes, no? Right. Right. Because we are saving, the incremental cost was negative, so we will be in second. Okay. So this is the way you actually do your PSC. Right? This is you will have thousands of iteration, you will plot them, and then based on your WTP, if the points are lying more in first or third quadrant, then you need to actually draw your WTP line and say that how many are lying above or below the WTP, and then you need to actually you don't have you actually compare your base case result with your WTP. The scattered the scatter plot actually tells you how uncertain your results might be. Maybe if your points are too much scattered, all like PSA is generating uh, results which which are there all over your graph, then it will show it that your model is not very robust. The inputs you are the model the inputs which are going into the model uh, are not correct, are not very credible. You need to look for further sources. You need to actually look out for further information on your inputs. Okay, so this is why you do the PSA, right? Now, let me first take a break here. I'll answer up your questions, and then I'll show you. This is a decision tree. Now I'll show you how Markov model, within Markov model, we do the modeling. Okay. I'll have an exercise for you with respect to decision tree analysis, which you have to do. So if you have any questions here, I'll not have PSA there, obviously, but for the base case analysis, you will have an exercise for sure. So if you have any questions, I'll take a pause, and please let me know if you have any questions. I'll stop sharing at this point. And I'm sorry, am I audible?
Yes, Akanksha.
There was something wrong with my connection, and I suddenly lost it, and now I can't see the questions. Can somebody read it for me?
Sure, I can.
Maybe. Yeah.
Yeah.
Thank you. Thank you, Rajpur.
So first question is from Namrata: how to decide which probability to take, and basically an aligning question with that is, if there are two literature giving contradicting probabilities, how do we choose?
Transition probability you're talking about?
Most probably yes.
Okay. So thank you, see, Rajpur. It's always better to first choose the publication which is more recent. You need to look at the data from which they are actually getting the probabilities. Is it direct? Is it any literature they are leveraging it from, or they are calculating it, or they are basically the transition probability is based on a patient level data which they have gathered. So we need to actually look back and see what is the source of their transition probabilities, right? And whatever looks more promising to us, then we adopt that. So it's never like uh, uh, that we blindly follow whichever is available. If we have comparative values, we need to see which has more robust calculation behind that, and then we need to take that accordingly. Okay.
Okay, so
Next question, please.
next question is, how do we get cost data for individual parameters?
Again, as I told you, like for migraine, you have recurrence, no recurrence. As since we are not clinicians, we don't know that how these events are managed. Okay, there, if it is publicly available in like if the claims database is available for patients managed migraine patients who are coming for recurrence, how they are managed, or if patient level data is available from electronic medical records, we can leverage that. Okay, the management can be leveraged from it, and then you can put the in the unit cost to the resources and unit cost to the services provided, and then you do the micro costing. Or if there is published literature, if you are lucky, you can get published literature which have the cost exactly the way you want. If you are lucky, it's very rare to find. Okay, the other way could be you find out the key opinion leaders, the doctors in your in your geography for which you are developing the model, and then you ask them how do they manage the event, and then accordingly you do the microcosting and report. So these are different ways you can take. It's by either whichever is like feasible, you can do.
Okay, next
Next.
question, how do we decide with a distribution to go?
Okay, for distribution, there is a set of basically a rule um, available. Like for example, you say for probabilities, transition probabilities, or event rates or utility values, you typically use beta distribution. Okay, and for cost, you use gamma distribution and log normal distribution. If it's skewed, because cost data could be skewed, right? And probabilities and all those parameters which range between 0 to 1, we usually use a beta distribution for them. Then for risk ratios, odd ratios, usually you use log normal uh, distribution. uh, for yeah, so usually by parameter, by type of variable, actually you can use these types, or maybe by the data which is available. If you have data by mean and standard deviation, you can use formula to derive. Basically you can actually see for beta, gamma distribution, right? So like this. Mainly, what I have followed is by parameter type you choose. It mainly makes it easier for doing the analysis.
Okay,
Okay,
so next question is, in what cases is PSA used?
every time. So when PSA actually helps you to determine the robustness of your model, how acceptable your model is, how credible your model is, right? If you are presenting results without PSA, people might question, especially when you are presenting it for these reimbursement submissions. Okay, you don't have PSA results, you don't know the uncertainty around your inputs, so it's very important to have PSA done. For reimbursement submission, it's a mandate. You need to have your PSA results because it helps you to understand the uncertainty around your variables which you have used into the model, and it provides you with the reasoning. If you have used your inputs, it actually helps. It also actually helps to to make changes in your model. If you are using very vague inputs, or if the using if your inputs are very uncertain, right? You will have you might have very you know frightening probability PSA scatter plots. So in those cases, you actually have to revisit your all inputs and see where the what is actually causing this, and this actually helps you to build a strong model. Okay, so that's why PSA is very important.
Next question is why there is no WTP threshold line in ICER plane.
Here in the example which I showed, I just created the ISO plot to show you how it's created, and only 25 iterations were there, so I did not plot it. Okay, WTP is line is mandate to be plotted. Actually, you have to have it when you have thousands of iteration to actually show that how many are lying below the WTP line. Or there are cases when all the lines, all the if your results are very, if your inputs are very credible, then all the dots of the scatter plot will lie below the willingness to pay. Sometimes you will find the line your scatter plot lines all along, like in all the four quadrants. So WTP line is important to be made, but here I have not done it because it was very few iterations I've shown you.
Okay, next question. Ma'am, in which case we should go for gamma distribution? Ma'am, if data is negatively skewed, then which distribution we should go for?
If it is skewed, if
Negatively
it's
skewed, the
if
question.
it's if it's maybe if you are saying it's less than zero, right?
Yes.
If it's
Listen.
less than, yeah. So in that case, you use negative, like log normal, right? Gamma distribution. This is what I, yeah, log normal and gamma distribution is mainly what I will prefer.
Okay, next question.
Okay.
Can you repeat about robustness of a model based on sensitivity analysis?
Yes. Sensitivity analysis actually helps you to determine how robust your model is.
So that was the last question till now.
Okay. Thank you. It means you were actually listening carefully. Thank you for that. Okay, so now I'll show you a Markov model. And somebody asked yesterday, like, how do we actually do cost effectiveness model, cost effectiveness analysis using Markov? So I just wanted to show you also that also, so that you are clear that this is the way how Markov trace is used. Okay, so let me know when my screen. Let me know when my screen is visible. Uh,
Yes, visible.
okay. So this is another model quickly done to basically show you how we do cost effectiveness analysis using Markov. So hope it is clear that when to use a decision tree and when to use Markov. If you are having chronic disease where stages are reoccurring and there is no unidirectional pathway, mostly Markov is the one to go. Okay. So here, if you see, I'll zoom it in. You have four different health states for a particular disease. Okay. Chronic silent disease, chronic active disease, death, or complications. Okay. And you can see the direction of movement of patient. So if there is chronic silent disease, the patient can go to the active state, death, or he can have complications, right? And if the patient is active, in the active disease stage, either he can go back to silent disease, or he can die, or he can have complications. And death is a dead state, so no patient moving from that. But if patient has complications, he can also go to death state, and there is no going back from complications. If you see, There is no going back from complication to silent disease or chronic active disease, right? Based on this, we have created our transition uh, probability matrix. Transition probability matrix. Okay, where a patient staying in the same health state in a silent state is this. From silent to active would be this. From silent to complication this, and death this. Similarly, from other to from active to silent, active, complication, death, and then similarly for other two states. Okay, the movement is captured in transition probability matrix. Now, apart from probabilities, what we will have? We want to have the these are probabilities again. We have actually done the naming of the probabilities to make it easier. Then we have cost, right? So cost for each health state for treatment A with treatment A and with treatment B. Okay. So you will now you would ask me that how do you get this cost? Again, with treatment A, how the management will happen? Like uh, it is assumed that treatment A and B can be given at all the three levels. Okay, and each treatment will have its own efficacy, will have its own success rates. Maybe the adverse events would be less, maybe the management would be better, patient would be better. So the cost in treatment A looks relatively lower than the treatment B. Okay, so again, for each type, for each health state, you need to, in detail, look into literature how this state is typically managed. Okay, what all healthcare services are given, and then you have to segregate it based on the treatment, where the treatment A and B comes into picture, and you have to apply the cost accordingly. Okay, then you have the utility values. So values we had per year utility values. Usually the values utilities are reported. The qualities are basically reported annually. So we have converted them into per month because our transition probabilities were for per month basis. So transition probabilities which we got were for monthly uh, monthly basis. So we had to convert the values to per month. So you can see here I have divided the value to 12 to get monthly values. Okay, we have utilities for each, and then we what discounting you want to use, what value per quality. Like if you want to actually change the qualities to monetary value, if we want to see the cost benefit ratio, if we want to monetize the qualities and we want to see the cost benefit ratio, then this will be important. Okay, now here comes our transition our probability matrix, our Markov trace. So you will have different sections. Firstly, you mentioned the year, the model. So you have to determine for how many years you are going to run the model. Here, for just for the purpose of explaining, I did it for 5 years. So the model is run. The macro trace is developed only for 5 years. So you have first you will have a column of number of years. Then you have the cycles. Let me just put it cycles. So this is a cycle length. Okay, cycles, not cycle length. Number of cycles you will have, because the transition probabilities you have are monthly. So you will have 12 cycles in a month, in a year. Sorry. Okay. So year, if you see, cycles is 12, and then from year one, in year one onward, you enter into next year, and cycle is 13. Okay. Now, in initial year, it was assumed in initial when model is when model began, it was assumed that all the patients entering into the model are active, right? And then you apply the probabilities. How do you apply the probabilities? You multiply the number of patients in previous year, like previous year, in each health state with the number of patients expected to move to silent health state. So 0 multiplied by transition probabilities of staying in 0, patients who are going to moving to active, moving from active to silent, moving from complications to silent, and moving from death to silent, which is not possible. Okay. Then for second row, second column, the same thing you will do. You will multiply the number of patients in previous year in each health state with the transition probabilities. So number of patients who are coming in active health state from silent, from active, from complication, and from death. Next, same is done for complications. Okay? You multiply the previous year patients with the transition probabilities. And then at the end for death. Same. Now, for the second, for the third cycle, your base patient you will take will be from previous year. Same formula, just the patient now you are taking from a previous year. Okay. So the same Markov trace which I showed you yesterday, it was for HIV. This is for another disease. The methodology is the same. Now here you have also you can also see the discounting is being applied. So for first year there would be 0 discounting within like the year when you are actually starting the treatment, you won't apply any discounting. From second year onwards you start applying the discounting. So here we have mentioned the discount rates which you will be applying. Okay, which will be applied basically, so we can directly put it later. Now, once you are done with number of patients within each health state, you will do the costing. Now, what you need for cost effectiveness ratio, you want to have the total cost and total uh, your qualities, right? Now we are going to do the total costing. How will we do that? Now, in first year there is no patient in silent health state, so the cost would be 0, and all the patients are in active health state. So you will multiply this number of patients with your cost from cost of management in this health state, right? So you are multiplying the discounting also here, and then the cost for management of active health state, this cost, right? Then you will again number of patients in active in complications, and multiplied by discounting, multiplied by the cost. So this is how you actually put up the cost, right? For all the number of cycles you have. I've done the same formula would be applied. Okay, the number of patients from the Markov trace multiplied by the cost, and if you are presenting the results with discounting, you multiply it with discounting also. Okay. Now, after cost, I've also given you all the outcomes. So now you have to basically also know how many qualities are applied for each health state in every cycle. So again, the formula would be same: number of patients in each health state multiplied by the your utility value, your qualities. Okay, so utility of your silent patients multiply by your number of patients multiply by discounting, because here we are doing the discounted values. Okay, sometimes or most of the times, what we do is we do report results without and with discounting both. Okay, with discounting is mandate, but you do provide results without discounting also. Okay, the formula is same here. The outcome, the utility value is replaced by cost. In the previous this section, we were actually multiplying the cost with number of patients. Here we are multiplying the utility value with the patients. Okay, with for each cycle you have your utility values. Utility you have number of patients for each cycle within each health state, and you multiply them with the utility value, and this is how you will get the utilities total. Once you are done with number of like all this calculation for all the years, okay, you will provide the final results. How would you do that? You would sum all of the results. Okay, so you will actually sum the results for each health state, right? So this is basically, this is the number of patients. These are the number of patients which should be these are the number of patients which should be one actually. Okay. Oh, these are discounted, so it should not be one. Sorry. If you are doing it without discounting, if you do the sum of all the the all these values in different health state, it should be one, because at the beginning when you started the patient number was one. Here I can also turn it to 100 to make it less uh, confusing. So let's start. We had 1,000 patients at the beginning of the analysis. So if we were doing the analysis without without discounting, the value should have been 100, not to. Okay, let's keep it to one. Then we have you do the sum. The next step, after you made the Markov trace, you would put the add the cost to you will create another section where you will put all the cost. Then you will make another section where you will put all the qualities or your effectiveness measures, right? Once you have done that, you will do the total costing. So you will add all the cost, right? You will add the total cost for treatment day. So this is the total cost for treatment day. First state A for your health state, silent, active, complication, and death. You will sum all of them, and similarly for your outcomes, you will sum all the. Once you have done that, so here I've also shown you a half cycle correction thing. So it is something which if you are not providing half cycle correction, the model will apply all the transition probabilities and all the utility values at the end of the year, not at the middle of the year, and it will impact the final results. Okay, and it's always good to do the half cycle correction when we are actually doing Markov modeling. Okay, so what you do is you the formula is a bit different. So how would you do it? You leave the first and last year, and then you multiply it with multiply the total with 50.5 50% basically, to apply the cost and the qualities at half at center at the middle of the year. What you know, what how do we correct it is, we see the formula here. I have left the initial first year, and I have left the last year. Okay, and then I have multiplied both of them with 0.5. So I am removing the first. a half of the first year and second half of the last year. And this is the way I'm trying to do the half cycle correction. So there are also a few other formulas also for it, but this is the way I prefer doing it because I've been doing it that way. Okay, so this is how you actually correct your model for half cycle correction. And so you are applying all the transition probabilities and utilities midway of your year, and see the results. There would be always a difference. Earlier, the total cost was 15,809. Now the cost is 15,885. Okay, so it's good if you can present the results with or without half cycle correction. It's always done. It's always good basically. This is treatment A. Similar exercise you will do for treatment B. Okay, and then you do the incrementals. Once you have the total cost for treatment B also, you again the same thing. You do the difference of the two, the difference of the cost divide by difference of the effect, and then you get your incremental cost effectiveness ratio. Okay. Any questions? What is the rate of discounting considered here? The rate of discounting considered here is 3.5, which was mentioned in the table here. Discount rate is 3.5. Let me show you the formula again. You won't see it because I have linked it directly to this. 3.5 is the discount rate. Okay. Can you please explain half cycle correction again? Okay. So, when we are actually, see, why do we want to do half cycle correction? If we are not, so the Markov model assumes that the event, everything, the event is happening, or the transition of the patient from one health state to another is happening at the end of the year. If we are not doing the half cycle correction, okay, but it can happen actually at any point in time, right? Within 1 year of span, it can happen actually at any point. But it is more suitable if we are actually assuming that it happens right at the middle of the year, because then it the variation would be not too much for all the events. Hope you are getting it right. So uh, to basically remove that bit of error in the modeling assumption, we use half cycle correction. Okay, hope it is clear. Anything else? This I think we are done with this. I have tried to explain you. See, it's very difficult to actually create a model within 2 hours. Okay, so I tried to explain you as much as I could within this time span. That's why I prepared the model already so that I can show you how you can actually do it by your own self. I'll share an exercise with you, and based on because we have to do an evaluation, so we have an exercise prepared for you, and I'll share that with you. And on the similar lines, you can actually try to do it on Excel. Okay, Excel is the Excel. Now, with respect to decision tree, you can also use triage, and triage is very helpful. It's very easy to actually do decision tree analysis on triage and also Markov. But because it's not freely available, everybody doesn't have access to it, so I've avoided it. Nowadays, there are also R is being used nowadays to basically do these type of modeling. But again, those are dependent on codes. You need to learn the coding for it, like R specific codes for it. So yeah, Excel is still being accepted by the reimbursement bodies, so that's why I preferred to show it over the Excel. Any other question? The floor is open. If you have any question, any question, please do ask. We'll be happy to answer. Um are the cost also there? Yes, per month. When you have, see, the way your cycle lengths are, the patient will be moving in that way. Okay, and for that, the flow of patient would actually depend on how your cycles are made. If they are monthly, you have to calculate of the cost of health states in months only. Otherwise, there would be over assumption of cost. If the cycle length is 6 months, the cost you are putting into the model have to be biannually. It would be helpful if you can share the Excel sheet of the model. Sorry, it's we can't share the model Excel sheet, but if you really want to do it, there are models available online, and you can actually try to replicate those. What are the rate of, okay? Can name some disease suitable for Markov modeling. There are a lot of disease areas. So I've seen Markov for diabetes. I've seen Markov for cancer screening. I've seen Markov for COPD. Any like they have many. So you can actually help use Markov for a number of diseases. Also, yeah, also for different autoimmune diseases. I hope that answers. Any other question? No more questions. Any other questions? Can you please share from where to download the examples and on where we can build the model as you just suggested? You just discussed. Can you please share from where to download the examples around? See, there are different organizations. I will have to also search. So earlier, when I was learning, there were websites, there were universities, and they had models available to learn. What point should I keep in mind while creating a model? See, as I told you earlier, let me just reshare that again with you. What you want to have, what you want to actually keep in mind when you are constructing your model. Let me know when it's possible. Once you have defined your research question, this step, defining your model framework. Okay. Uh, First, you need to know, like, first of all, you have to know your disease area, your drug in and out. You should have thorough knowledge about your disease and your drug. Okay, at what level your drug is actually working, what population it caters to, is it gender specific, is it age specific? Okay, you need to know about and Is there any subpopulation in a disease only which it is targeting to, things like that? Because on that, on all these things, you actually start collating your evidence or your data. So, for example, if we talk about HIV, like the yesterday's example, HIV. So there were CD4 scores. There were different health states, and the CD4 scores, based on those CD4 scores, the health states were actually captured. And if CD4 score is more than 500, it was not even included in state A, right? The state A was between 300 to 500 per cubic centimeter, your cell, CD4 cells. So maybe the drug can only target to those population who have this much lower CD4 score, things like that. Also, when you're constructing a model, you need to have data, right? So first point is, you define the model framework, you know your disease in and out, you know your intervention in and out. Then you start thinking about what perspective you are actually looking at, because all the cost will be from that perspective. You have to think from that perspective, what all cost can be included, right? Because here in all the models, I have provided you the upfront cost, that this is the cost which will be applied. But if I talk about a health state here, if I talk about health management of a health state, from different perspectives, from societal perspective, from a healthcare perspective, the cost would vary significantly, because the cost which is from society, from societal perspective, it will have all types of like direct cost, indirect cost, and maybe if you are talking about the, if you want it from the payers hospital perspective, provider perspective, then they will only, you will have to only focus on those costs which a healthcare provider is is paying, is actually delivering, what all services, what all costs he have to incur. The cost a person, a patient who goes to a private hospital, private diagnostic center for his test, cost of that test would be very different from cost which actually a hospital is paying for that particular test, right? So in this way, the perspective is very important. Then comes your time horizon. How long, if you have Markov model, how long you want to run your model, or you want it for lifetime, you want it for 5 years, 10 years, 20 years, and what rationale you have behind that. Then the type of model again, you need to determine which model would be best. Sometimes it's not only like you have Markov, you have mixed model also. In the beginning you have decision tree, and at the end you have Markov. So there have been cases where there is combination of models. Okay, then you have you want to know the which platform you want to have, and then again, evidence related to your model, evidence related to your disease, your drug, your comparator. Do you have direct evidence of comparison, like clinical effect? Do you have comparison? You have studies which compare your intervention with the comparator directly or not? We don't have things like that. Needs to be very thought of, like thought of. If you don't, if you have a, for example, if you have a very naive treatment, naive therapy in for a rare disease, what will you do in that case? What would be your comparator? Now you tell me. If you, if a pharmaceutical company has launched a very naive disease, naive treatment, very new treatment for a rare disease for which there was no treatment as such earlier, what is your comparator? What will you do in such a case? Yes, correct. The standard of care which is there, like how patients are currently managed, that would be your comparison in that case. Okay. So these are main things when you are creating your model. First, once you know your disease very well, the model framework, the flow of patient from which health state to which health state, you have to be very thoughtful of that. Try to leverage the information from previously published articles if you have, because that helps to create your own, your own model framework. If it is not available, go and read the progression of your disease, how it's progressing. Doing nothing, yes, doing nothing is also one thing, right? You don't do anything. This can be a competitor too. But then you won't have any cost. Would you have any cost for doing nothing? Okay, question. What cost would you apply when you have a competitor of doing nothing? Yes. If you have society perspective, if you have patient perspective, yes, correct, absolutely. Okay, any more questions? Over to you, Rajpal.
Okay, thank you. So thanks everyone. So I will hand over to Fatima for the closing comments.
Yes, sir. Thank you so much, everybody, for joining today. We had such an insightful session. And don't forget to explore what you've learned today, revisit yesterday's notes, and most importantly, don't be afraid to model and make mistakes. That's how best models are built. Until next time, stay inquisitive, stay inspired, and good night from my side. Thank you, ma'am. Thank you, sir, for an incredible lecture.
Thanks
Thank you.
everyone. Bye-bye.